Physics 101, static equilibrium problem set, number 7. We have a beam. The beam has a mass of 80 kilograms per unit length. Now, this is the first trick. There's essentially two tricks in this problem where the author of the problem is trying to fool us. And this is the first one. He says the mass of the beam is 80 kilograms per meter. So it's not 80 kilograms, it's 80 kilograms for every meter of length. And since we're given a length, it says D equals 5.870 meters, we have to take that 80 kilograms per meter and multiply it by the number of meters, which in this case is 5.870. And that's going to give us our total mass of the beam. Now, I'm sure your numbers are different than the ones that were given to me, but that's how you find the mass of the beam. All right, that's important. Next, we know the tension, the maximum tension in the cable. Not maximum, it's just the tension in the cable. It's going to be going up like this. That's the tension. We're trying to find the weight of the load. We know that the gravity on the beam, it's a uniform beam, so it's going to act right in the middle. And there's going to be a force at the pivot point that's going to counteract some of those other forces. And I'm making a guess. I'm guessing that it's up and to the right. If it's not up and to the right, when I calculate the components of it, I'll find negative numbers. So that's what we're finding in the second part. The first part, we're finding the weight of the load. Just before the system breaks and it won't be at equilibrium, it is at a static equilibrium, so the torques are equal and the forces are equal. And that's how we're going to solve these problems. The second trick, I said there was several. The second of the two that I'm aware of is finding this angle. Now, in blue here, I'm going to make the triangle that connects that angle. This is the key to finding that. One side of that triangle is h, the height of that far side. The bottom part, though, you'd be tempted to use d, whatever the given value for d is, but it isn't, because the cable doesn't go all the way till the end. So that bottom side of the triangle is d minus s. So to find theta, we have the opposite, which is h, and the adjacent, which is d minus s. So we're going to use the inverse tangent of the opposite over the adjacent. All right, so writing down all the stuff that we know, we have the theta, we have the mass of the beam, and we can find the force of gravity on the beam. So I'm just going to call it force of the beam is going to equal the mass of the beam, which you got up at the top there, times g. We also know the distance d, we know the height h, we know the distance s, the distance x. Those are all given in the problem. So we have our beam, we have our load, we have the weight, the gravitational force, we'll call it the force of the beam. We have the tension acting at angle theta, and we have the force on the pivot. Now, I'm choosing my pivot point for the equal torques to be the pivot point. It's a convenient spot because it eliminates one of our unknowns. The force of the pivot we don't know yet. We're going to find it later. And I'm going to use the fact that the torques are balanced to find how much force that load is applying. So the clockwise torques are going to equal the counterclockwise torques. In the clockwise direction, we have the torque from the beam plus the torque from the load, and that's going to equal the torque from the tension. For the beam, we have a distance from the pivot of d divided by 2. For the load, we have a distance from the pivot of d minus x. And for the tension, we have a distance from the pivot of d minus s. So the the torque from the beam is going to be the force of the beam times the distance from the pivot, which was d over 2, times the sine of the angle between them, which is 90 degrees, but that just becomes a 1, plus the torque from the load, which is the weight of the load, which we're trying to find, times the distance from the pivot, which is d minus x, times again the sine of 90 degrees, which is just 1. That's going to equal the torque from the tension, which is going to be the tension force given in the problem, times the distance from the pivot, which is d minus s, both of which are given in the problem, times the sine of the angle theta, which we found, I showed you how to find on the last slide. So this is just a number, and this is just a number, and this is just a number. The only thing that we don't know is the weight of the load. So you can plug your numbers in and solve for the weight. For the next part, we're asked to find the force of the joint, the force at that pivot point. So the beam is attached to the building, so the building is going to be applying a force to the beam. So we have our beam, we have this force of the pivot, we're asked to find that. We're going to have the tension force acting over here at angle theta. We're going to have the weight of the load, which we just found, and the weight of the beam. So force of the beam. We know that in the static equilibrium, all the forces are equal to each other. So we have force in the in the x direction, we have the force right is going to equal the force to the left. The net force is 0, so whatever is going in the positive direction has to equal whatever is going in the negative direction. In the positive direction, we have the x component of the force at the pivot, so Fp sub x. In the negative direction, we have Ft in the x. So those two things have to be equal to each other. Fp in the x direction is going to equal, well, Ft in the x direction is going to be Ft, the tension is given in the problem, times the cosine of our angle that we found before, theta. All right, that's it. You know what the tension is and you know what theta is because we figured it out right at the beginning. In the y direction, we have the forces up equal the forces down. Once again, net force is 0, so they have to add to 0, which means that the positive forces have to equal the negative forces. So what forces are going up? Let's switch to yellow. I haven't used yellow yet. We have Fp in the y direction, and we have the tension in the y direction. So we have Fpy plus tension in the y equals the forces down. There's two forces down. We have the force on the beam, gravitational force of the beam, plus the weight of the load, which we found in the last part. So I'm going to solve for Fpy so that I can get the y component of Fp. Fpy is going to equal force of the beam is m of the beam. We found that right at the beginning, times g, plus the weight of the load, which we found in part 1, minus the tension in the y direction, which is going to be the tension times the sine of our angle theta. Awesome. Now we have the two components. We're asked to find the magnitude of that force, and we have the x component, Fpx, and we have the y component, PY. From that, using the Pythagorean theorem, we can find that final side, and that's all we need, FP.